So apparently there was a sound problem, I think. So let me do that again. So hello everyone and welcome. I hope that you had a nice lunch. My name is Jonas Unger and I will be the chair of this industrial keynote session. And the first industrial keynote speaker this year is Dr. David Lübke. He is the Vice President of Graphics Research at Nvidia. And Nvidia is also one of the main sponsors for the Eurographics in Eurovis 2020. Dr. Lübke received his PhD from the University of North Carolina in 1998, and he spent 8 years as a faculty member at the University of Virginia. In 2006, he helped found Nvidia Research, and he has made numerous contributions to the field, and especially in augmented and virtual reality, real-time rendering, and he is now working at the intersection of computer graphics and machine learning. And with that, I would like to once again welcome our first industrial keynote speaker and hand over to David Lübke, the Vice President of Graphics Research at Nvidia. And I would also like to encourage you all to ask questions on the YouTube channel and over Discord. Thank you. Please go ahead.
Hi, everybody. I'm Dave Lübke. I am the VP of Graphics Research at Nvidia. And let me tell you a little bit about us. We are part of the larger Nvidia research group. Graphics Research is 43 full-time researchers at last count, plus a handful of interns and postdocs. We're sprinkled across 11 time zones representing North America and Europe, and we're organized into 4 groups. Those groups are real-time rendering research, which focuses, as the name suggests, on real-time rendering, such as you might find in video games and other sort of real-time applications. New experiences, which again, as the name suggests, focuses on sort of new visual experiences. This could be, for example, cloud graphics, streaming graphics from the cloud, or augmented or virtual reality, or extremely low latency graphics, such as you might want for competitive gaming and esports. Mathematical foundations of graphics and related applications of those ideas to things like machine learning and wireless networks. And neural image synthesis, which is the heart of what I'm going to talk about today, but one of the points I want to make is that even though we've got these sort of 4 groups, in fact, there's heavy overlap in people and in projects, and overlapping all of this is this idea of using deep neural networks. So this talk is really about the intersection of artificial intelligence, meaning in this case deep neural networks, with all these different fields or subfields of computer graphics. I'm going to start by talking a little bit about texture synthesis and style transfer. Really, I just want to kind of remind you that there's been this really nice sort of line of work, this body of work that goes back in some ways to the 80s, but has been really revived and made practical by deep neural networks by the work of Gaddis et al. And in people who have followed. The basic idea is to take the sort of statistics on the feature maps that you get when you apply a neural network to a given image, pre-trained neural network to a given image, take the statistics of the resulting activations on those feature maps and use them as sort of a statistical fingerprint of that image. And then you can turn around and enforce that statistical fingerprint, enforce those statistics on the feature maps of another image, and you can evolve that other image to look like the image that you started with. So this can be used, for example, to evolve a field of random noise into a texture of potatoes or pasta, or it can be used to evolve one image to contain the style of another image. And this connection between style, meaning, and these statistics of feature maps in a neural network is one that we're going to come back to later on in the talk. So this has been used to make really beautiful artwork. I could show you countless examples, but you've probably already seen many such examples where you take, some sort of target image, which is sort of the content, in this case, this photograph of Half Dome, this iconic rock in Yosemite National Park in California, and apply the style of another image, in this case, this famous painting by Van Gogh, to get an image that seems to blend the attributes of the two. So all kinds of really cool kind of artwork has come out of this sort of collaboration between a computer and an artist. The artist's job is to pick the images and maybe tweak the parameters, and then the actual style transfer is done by the neural network. and an optimization framework. So that's backdrop. That's definitely one of the first way I would say that neural networks really impacted computer graphics. These days, the landscape at the sort of frontier of artificial intelligence and computer graphics, I sort of mentally break it down into three main categories. And the first of those is neural rendering pipelines. And this is a broad class of neural graphics that exist right now that are really focused on sort of adding or replacing components in the graphics pipeline. So neural networks have been used for texture, for visibility, for anti-aliasing, for estimating irradiance, and for upsampling in space and time. That's just to give a few examples that come to mind. Let me show you a couple specific examples from Nvidia. The first one is this work called DLSS. So DLSS stands for Deep Learned Supersampling, and it's kind of a combination of an anti-aliasing algorithm with an upsampling algorithm. So the image on top is the full resolution image. I believe this is a detail from a 1080p image. And you can see that the anti-aliasing isn't fantastic. So for example, if I turn on my sort of laser pointer and highlight this area here, this grading back here is a little blurry. Same with this grading back here. Compare that to the image, the corresponding areas down below, and you can see that these images down below look a lot better, even though they are actually coming from a much lower res image. And so the result is that this image on the bottom, even though we are running an additional neural network that takes up some of the frame time, actually renders 30 to 100% faster than the image on the top. And that's because it's a considerably lower resolution image. So we're using essentially a deep network to help predict, to help do temporal anti-aliasing, to help decide which samples contribute how much from previous frames to the current frame. And this has been an enormously successful product for Nvidia. It's been applied to dozens of games, maybe hundreds of games by now. And DLSS 2.0, which just released, has gotten rave reviews. It really does make your games look better and run faster. And that's sort of kind of hard to beat. So in this case, the examples that are easy to see are the antenna on the white building in the sunlight on the right-hand side of the image, and some of the details on the windows, for example, in that building. Again, the bottom image is rendered at lower resolution, but it looks better because we're more intelligently incorporating samples from previous frames. A similar concept is being applied by a lot of people right now for denoising path traced images. And we actually believe that path tracing really is, or some derivative of path tracing, is going to be kind of this unified rendering algorithm that's going to take real-time rendering kind of by storm. We think that this is really the future of real-time rendering, where unlike in film, where you can afford to trace 1,000 or even 10,000 paths per pixel, even with hardware-accelerated ray tracing today, you're lucky if you can trace, 1 or 2 or 5 samples per pixel in a path tracing in real time. And so that leads to really noisy input. And so the question is, can you train a neural network to denoise that input, to recognize that noise and extract the underlying signal? And the answer is yes, you can. The frontier of this is, again, making use of temporal information, so integrating samples from over multiple frames just to get enough data to work with. And this is really critical, as it was with the DLSS. And the reason I want to highlight this is that this is actually a paper that's going to be presented at Graphics later today. So this is Neural Temporal Adaptive Sampling and Denoising by Jan Hesselgren and others. And it's really doing sort of joint sampling and denoising. In other words, the denoiser is not only producing a cleaner image, taking the samples and producing a final image, but it's also sort of then informing the sampling algorithm and saying, okay, we need more samples here. And that sampling algorithm, again, is sort of incorporating samples from over space and time. And so this idea of sort of joint temporal adaptive sampling with denoising is a really powerful idea. We think this is the future, honestly, of real-time computer graphics, some variation or derivative of this. So those have been very successful. This sort of neural rendering pipelines where you replace or add a component to the standard rendering pipeline, that's been very successful. It's successful today. You see it in film rendering, you see it in real-time rendering with DLSS. Then there's a more ambitious class of neural graphics algorithms that are trying to represent the shapes of the models or the scene graph or the way that light moves around in the scene using a neural network. And I don't have an example of this, but differentiable rendering is a very hot topic right now, and it would fall into this category. So let me show you a couple of examples of work that we're doing at NVIDIA here. So again, going to path tracing, as you know, path tracing, bounces, light rays, sends rays out of the camera and sees what they hit, and then bounces those rays all around the scene to try to gather up the light. And you hope that these bounced rays eventually land on a light source, and then you can compute how much light comes from that light source along that path into the camera. What we did is we took a neural network and we trained it from the light paths to predict the light field of the scene. So we shoot a whole bunch of paths, and we train a neural network to take information about the hit point and predict the direction that the light, the excident radiance in a particular direction. So now we can trace primary rays, then take the hit information such as the 3D position and the view direction and other things that you would feed into a G buffer, pass that information to a neural network, which then will predict the final excident radiance back toward the camera. And to my surprise, a neural network can in fact be successfully trained to predict the light field even in a fairly complex situation. So this is exactly what we're seeing here. We're rendering full global illumination at interactive rates using just primary rays and a neural network. Now this is running fairly slowly. It actually takes 1 frame per second. I've sped it up for this movie. But we think we can improve this quite a bit. And then it's not perfect. You can see that it doesn't do a perfect job on that difficult teapot on the left, but it does a pretty good job, and we think we know how to improve this in a provably unbiased way. So that's one piece of work we're doing, where we're sort of representing the light field with a neural network. Here's an even more ambitious concept, and correspondingly sort of at a more primitive state right now. That's part of this body of work that has started, that people have started working on, where you represent the entire scene in an end-to-end fashion inside a neural network. So the neural network learns, you don't give it a geometry representation and a material representation like a BSDF and a lighting configuration. You let it learn all of those things end to end from a bunch of observations. And this is a SIGGRAPH paper that we have coming up this year that works on this. Essentially, you take a bunch of observations, such as you see on the left, and then you render it, you give it a G buffer, and you ask the network to produce images that match the observations and the G buffer, and it works remarkably well. So here's an example of a more complex scene where you can see that we're flying around, and you can see that the reflections and the highlights kind of do the right thing. Even if and then we change the observations, we get a different look. Even the mirror kind of does the right thing, which is remarkable because remember, no rays are being shot here. This is entirely based on learned information. So this is very exciting work, if very early, and it's very holistic, right? You're using the network to replace a whole lot of stuff. The final category that I want to talk about goes all the way. So now we don't even have a representation of the scene. We're simply giving the network either some sort of input, which might simply be random numbers, and we're expecting it to produce an image. And so this is what I'll call neural image synthesis. Obviously, that term could be used, to reflect all the things I've talked about, but I'm using it here to reflect this kind of image synthesis. And this breaks down into kind of two main categories: conditional image synthesis and unconditional. Conditional image synthesis is sort of epitomized by this program called Gauguin, which NVIDIA has made. And you may well have seen demos of this. It's one of our sort of really successful kind of cool marketing demos, and it's really fun to play with. You can actually go online on their AI playground on NVIDIA's website and just explore this on yourself. But you basically do this sort of paint by numbers, where you draw a scene, a semantic segmentation of a scene, and we've trained it on a bunch of semantic segmentations of landscape photos to produce things. Let me show you a short little marketing video that NVIDIA made, because I think it really drives home this idea of an artist and computer collaborating, and how a program like Gauguin can actually be a useful tool for this.
Gauguin is like a pen by numbers. Users just need to put some color on the canvas, and our deep learning network can convert users' doodles to photorealistic images. Software developers, designers, even leading artists are using Gaussian to inspire them for their projects. It's totally crazy. Artists are using our app to create new art.
What I'm excited about with Gaussian is that now I may be able to integrate a mood early on into this, and an environment, not just vehicle first, environment second. And for the first time now, I'm starting to think, wow, well, I should really maybe just jam out an environment really quick and then paint something in it, because it allows me to iterate so many different ideas. It's not something that I ever imagined having at my disposal. This kind of popped on the scene and has interrupted my notion of what I might be able to use to give myself new ideas. And for me, it's about how much more inspiration can I get.
I think that's a good place to stop. So again, this is really being used. This is really being used in practice by artists, and I think that's super exciting. So that's one end of the spectrum, right? I'm literally providing sort of pixel by pixel guidance to the algorithm. And the result is conditioned on, in our case, this semantic segmentation map that says rock here, sky here, cloud there. The other end of the spectrum is unconditional image synthesis, and that's epitomized by the StyleGAN work that we've done. And I'm going to show you some examples. But StyleGAN, again, you've probably seen some of these results. Is really just a bunch of random numbers come in our case 500 random numbers, and a megapixel image goes out. This is part of a body of work that really started in earnest in 2014 with Ian Goodfellow's seminal paper on generative adversarial networks, or GANs. And these results were sort of shockingly good at the time, but now we've reached sort of a new level, right? So this is the result of a StyleGAN 2, which is a refinement to our StyleGAN algorithm that I would argue is approaching film quality. You really have to stare at this image for a while to sort of convince yourself that it's definitely not real. And again, you change the random numbers, you give it a different point in this 500-dimensional space, and you get a different image. And so we get fairly good diversity. You see, fairly good realism here. You have flaws in the skin. You have facial hair stubble. You have flowers in this girl's hair. Her hair color matches her lip shade. I can produce many more images. And again, the diversity is pretty good. Up to the limitations of our data set, diversity is pretty good. And so we see a guy with a bushy beard. We see people with strong lighting, strongly lit from the side. Indoors shots, outdoor shots, sort of glamour shots, photo shoots, casual, candid shots. So this does a good job, I would say, of capturing this sort of the diversity of photos that you find on Flickr, which is where we got the photos to train this with. And it doesn't just do faces. You can do this for cats and dogs and cars and horses. And again, it gives you pretty good results. These results aren't quite as good as the faces, but that's largely because we don't have quite as good or as uniform a set of training data. But now this interesting question is like, what about control? In the one case, I had to tell it pixel by pixel exactly what I wanted. And that maybe is requiring too much control in some situations. In the other case, I just gave it a bunch of random numbers and it made an image, and I didn't seem to have any control over whether that image was of a young person, an old person, a male, a female. But actually, there is a little more control than that, and that's kind of the interesting frontier of this research. In StyleGAN, the reason I talked about texture synthesis before and the style transfer, such as making that picture of Half Dome look like it was painted by Van Gogh, is to get across this concept of styles, where a style in that literature really means a set of statistics that are enforced on the feature maps of a neural network. And that's exactly what we're doing in StyleGAN. And what we find is that if we change the random numbers that influence the statistics of the high levels of the pyramid of our generative convolutional network, then we get changes in broad things like the gender of the photo of the person in the photograph, whether they have long hair or short hair, whether they're wearing glasses, whether it's a side shot, a profile shot, or a straight-on shot. If we change sort of the middle levels of the pyramid, the 16 by 16 and 32 by 32 layers of the pyramid, we get to change the facial attributes of the photograph. And the fine levels, which is the majority of the convolutional weights in the pyramid, in the neural network, really just kind of change the color scheme. Same subject, same pose, different colors. Here's a video that we released at the time that sort of shows this. I like this video. Well, it's a little confusing. So what we're seeing here is I'm manipulating the course styles in a way, and I'm generating one image, and I'm just taking the course styles from the course level of the pyramid, and I'm superimposing them with these middle styles, which I'm now changing, and those fine styles, which I'm next going to change. And what you see is that when you manipulate the fine styles, nothing changes but the colors in the image. It's like you were playing with sliders in Photoshop. When you manipulate the course styles, then you change major things like the gender, facial hair, glasses, long hair versus short hair, the camera pose. And the middle styles, you're changing the facial identity, sort of what makes you look like you, what makes you look like your mother. That's what's changing with these middle styles. So there is a level of control here. There's a level of separation, but it's a little difficult to hang on to. And this is kind of this, I would say that this is the interesting frontier of generative adversarial network, guide neural image synthesis. You can do things kind of manually. You can say, okay, here's a bunch of images, and these appear to be images of old people. And here's a bunch of images that appear to be images of young people. So you can kind of hand classify these and extract a vector in this 512-dimensional space that corresponds or correlates with the apparent age of the subject in the photograph. And then using that, you can cause, whoops, sorry. Come on. Trying to play this video. All right. So now here we can sort of move the points along that vector, and so each of these random points generates now a series of pictures that look from sort of going from somebody young to somebody old, and we can similarly do this kind of classification and guidance for smiling. We could separate out the people who appear to be smiling and the people who don't. And there's a lot of work on this, and you would call this kind of supervised control. And so there's several papers that I've pulled out here. Nvidia's involved in a couple of these, and essentially you're kind of limited by your imagination. And so I want to highlight this work that has just come out. So this is work by my colleague Jaakko Litmanen with his student Eric and Aaron and Sylvain at Adobe Research, where Eric was interning at one point. And the way to think of this work is that instead of saying, hey model, I'd like you to learn about smiling, or I'd like you to learn about age, it's sort of, hey model, show me what you've learned by looking at all of these photographs, all these different photographs. And so they have this nice video that sort of shows, I've kind of sped it up here, so it's a little frenetic, but the idea is that you're basically doing PCA in this latent space. You're finding the principal components, and then you're deciding, okay, look, this principal component corresponds to kind of how curvy the car is. This one corresponds, does it look sporty or does it look boxy? And what you can do then, once you've kind of discovered these, as you explore this space, you can give it a name and say, okay, this is the sports car slider. And now I can take any point in the space and I can kind of make it look more like a sports car, or less like a sports car. And so they have many examples of this. You can apply this to the way that to people photographs. You can say, okay, well, you can sort of discover the large jaw or the round mouth slider. You can control the lighting, and this is really cool because, of course, this thing knows nothing about 3D, nothing about lighting, nothing about materials. We certainly didn't go into this intending there to be a lipstick vector, but that's something that the system has learned by looking at a lot of photographs. And so this is very cool work. I want to do one or two more, refer to one or two other things. I want to point out, to make this really useful, this kind of system really useful. You'd like to be able to separate out the foreground and the background. And this is just a toy example. We never published it, but it's a good example of how we think about these problems. So we know how to do foreground-background separation, right? You have the generator make a background and a foreground and an alpha mask. And in computer graphics, we know what to do with that. You take the alpha mask and you multiply it by the foreground. You take 1 minus the mask, multiply it by the background. You add those together, and now you've got the over operator. But the cool thing is, if you have the generator make these images and this alpha mask, and then you apply this operator before you give it to the discriminator in the GAN, then the only way that the generator can consistently fool the discriminator is if it evolves to have this out to be able to produce a pixel-perfect alpha mask. And sure enough, that's what we get. So now here's a bunch of examples, and you can see that even the fine details of hair fibers, the whiskers on the cat, and so forth, the fur on the cat, they're all just, we've got pixel-perfect alpha channel, just by changing the rules of what we handed to the discriminator. We didn't hand it an image now, we handed it an image that had been composited. So this gives us a sense of like maybe where this is going. GANs today, basically you have a learned generator and a learned discriminator, and you generate images and you compare them to real images. And we think that GANs tomorrow are going to sort of broaden this concept. And instead of learning an image directly, you're going to learn a shape and a material and an illumination. And now you see the connection to some of the work I showed earlier where you're jointly learning those things. And then you go through a very conventional rendering process perhaps, or perhaps some sort of neurally accelerated rendering process, but you're basically rendering images rather than simply synthesizing them from scratch. And now you've got the control, because you still have a shape and a material and an alpha channel and all these other things. So we think this is kind of the direction that things are going to go. I want to close with just a couple comments in my last minute or so on trustworthy image synthesis. There's been a lot of work. This is not a new problem, right? People are very worried about things like deep fakes. They're worried about these GANs producing images that can't be discerned from reality. It's not a new problem. The image on the left is from 1840. It's the first known hoax photograph, and it's actually the first known fake news photograph, because this guy basically faked his own death and sent in a by sort of superimposing his own face on a cadaver, and sent it in to the newspaper as a way of complaining about his mistreatment at the hands of the French Royal Society. And there's the image on the right is sort of a coffee table book that is spooky and worth reading, about the falsification of photographs and art in Stalinist Russia. There's a lot of work right now out there, a lot of good work, that is thinking about how to do detection and attribution of fake images and sort of connecting images to the networks that produced them, or detecting them in the first place. This is all good work. None of it is bulletproof. None of it is really ready for prime time. We have our own contribution to this. We think about, with StyleGAN, we thought about what happens if we take an image and we sort of project it into the latent space of a network. Well, it turns out that if that image was generated by the network, you can project it into the latent space basically perfectly. You can find the exact point that would generate that image. And that is sort of perfectly good evidence that that image came from that network. That would be easy to explain to a jury. Take these 512 numbers and type them in, and you get that image. On the other hand, if you take images that did not come from the networks, these are real images rather than synthesized images, there are clear differences from the originals, right? These are not the same images, and in fact, the network cannot capture those images exactly, and that's evidence that this network did not generate those exact images. This is not a bulletproof forensic technique by any means, but it's an interesting direction to take, and I think we and a few other researchers have been thinking about this direction. So I'd kind of like to end on that. Just a call to action. There's a lot of good work on this. I think there needs to be more. Think about trustworthy image synthesis. Don't just think about generating realistic images. Think about detecting them. Think about characterizing their intent. Think about preventing misuse of those images, whether that's by watermarking or other techniques. I think this is an important thing for us to work on as a community. I'd like to thank the many people who did the research.
You'll go live in 10 seconds.
And thank you all for listening.
So, thank you, David, for a very nice presentation. I'm I'm trying to look in the Google chat here to see if we have any questions coming up. We have a few minutes left for questions. I should remind you that there is another keynote presentation starting in another session within the next couple of minutes, but I think there is time for some questions if we have any for David, either through Discord or the Google chat. No. So in that case, I have a question for you. There are so many impressive results that you have produced with in this, let's say, combination between graphics and machine learning and so on. And I'm particularly interested in the neural light field rendering. And I mean, based on the examples, I think it's incredible to see what results can be achieved. But how far do you think this can be taken, and how well, can it generalize and so on?
Yeah. Hey, by the way, can you hear me? I'm
Yes.
having to mute the YouTube stream and unmute on Zoom, so I want to make sure you can hear me all right. No, it's a good question. To what extent are we sort of overfitting that simple scene by training, by training, that particular light field, and does it generalize? And of course, when you to train a neural scene, a neural light field like that, you have to be able to sample the light field, and if it's a dynamic scene, and the lighting might change or something unexpected might happen, like in real-time rendering, then how do you account for that? I would say that the honest answer is we don't know yet. This is very much sort of an active frontier. I was amazed how well it works because there's just so much information in a light field. But of course, most of it is very low frequency. I think that's very promising. I think the next stage is you're also going to have to be able to incorporate the error. You're going to have to be able to sort of detect the error that is in the light field and incorporate it into, for example, by shooting more rays and finding discrepancies, and incorporate this into a light transport algorithm where the neural light field is a prediction rather than the final answer. And that's exactly the direction we're going with that work.
Sounds.
Let's see. Should I be answering directions directly off of the Zoom chat or the?
You can do that if you like.
Okay, so I will just go ahead and do this because otherwise I have to balance a couple mutes. And by the way, I understand there's another session. I know a lot of people are going to be dropping off and going to that session, but I will be happy to stick around here as long as there's questions. It's early in the morning for me. So Joaquin says, what about synthesizing geometry? And absolutely, I didn't. Unfortunately, that was the part I had to cut. We have some cool results on synthesizing geometry in the using neural networks, and a lot of other people around the world are working on this. A direction that we're particularly excited about, as I kind of alluded to briefly, is differentiable rendering. Right? If you have a differentiable scene representation and a differentiable renderer, then you can use the neural network and the training of a neural network to sort of evolve that geometry to be whatever you need it to be. And there's different levels that we can take this. If we want something that's going to be useful in the short term, we should simply create a mesh because meshes are what we know how to render, and we should find ways to move the vertices of that mesh around, in a differentiable fashion. If we want something that's sort of more forward-looking and maybe has more open-ended potential, but is probably going to take a lot longer before it can actually be incorporated into tools and workflows, then you start to open up these options of a completely neural representation for the scene, for the geometry, for everything else, and training it all in end-to-end fashion. So we're trying to work on sort of both ends of the spectrum. Do things that are useful now. I will say that if you're trying to build a differentiable renderer that's useful in the short term, we believe that a huge part of the problem is that most differentiable renderers are just way too slow right now to really incorporate into the training loop and deal with a complex scene. So I think that's sort of the frontier. Okay, great. I'm seeing the questions go. I'll just keep talking. Tell me on the Slack chat or the Zoom chat if I need to stop. I see the question, would you say texture synthesis should move completely toward AI? Okay, so here I'm not an expert in the texture, sort of the subfield of texture synthesis. My knee-jerk reaction is yes, it seems so promising to do this in sort of a deep learning framework that I have trouble imagining, why you wouldn't do that. But that's a pretty naive statement, really, because honestly, I don't know the field. I don't understand the pros and cons. Of course, the problem, as everybody knows, with these sort of deep neural networks is there's something of a black box, right? It's hard to predict what they're going to do. And even though they seem to work better than anything else, like, it's hard to know that for sure. And so when you want to exert some control over what the deep network does, it's a little hard to find the levers to pull on. And that's why we have so much work trying to understand, what is going on in this latent space. And I think the same would be true for texture synthesis. Certainly AI is going to be a huge component of texture synthesis. It's just such a powerful tool. One question I see is how many ground truth images are needed to train StyleGAN? This is another thing we're actively working on. So the answer is nobody knows. Like, we could sort of experimentally, add more images and stop when the results seem to stop getting better. But even determining when the results have stopped getting better is enormously difficult, right? It might take a week to train on a given batch of images, and then then you do it again and do some subjective test of whether it was better or not. So just even the metrics that you use is an active area of research. But to answer the question a little more directly, our best results are the ones of the faces, where we have this data set we call FFHQ, Flickr Faces High Quality. And FFHQ has 70,000 faces. We curated those by hand, via Mechanical Turk and the like, and found good photographs that were of faces and not pictures of paintings or pictures of statues or something. We have been working with pictures of paintings and pictures of statues, and that was another thing I had to cut at the last minute because I just didn't have enough time in the talk. But we have some cool new results using much fewer, more like a couple thousand images they're not as good. There's no substitute for data, but they're remarkably good given how little data to start with. And so that's, as I said, sort of another active area for us. And I did see one more question. When will this technology migrate down to off-the-shelf Nvidia cards? So the cards are off-the-shelf, like that you're seeing. It's a pretty expensive shelf in some cases. There's the very high end is, we just announced our newest product, which is a $200,000 8 GPU, enormous amount of bandwidth and memory and computational horsepower using the new Ampere architecture. But all the results I showed are trained on, conventional GPUs, sort of just the server equivalents of what you would go and buy, what you could go and buy at the store, and stick in your own machine. Now, in terms of the software libraries that we're showing, we are, actively working on technology transfer of some of them. A lot of this is more SDK and more the kind of thing that some software partner will incorporate, right? But there are a few examples, and if you just want to play around with them, a lot of them are showcased at this NVIDIA AI Playground. If you go to the NVIDIA website, it's fairly easy to find this AI Playground, for which you can launch a bunch of these demos and just run them in the browser. And everything I showed, I think, except the unpublished work, is available on GitHub. You can download it and use it for research purposes freely. And that may be all of the questions that I see. Oh, no, another one, a couple more showed up. Good question. So somebody says, hey, the art community could feel offended by some of the AI tools. What is your response? Certainly, I hope not. I think that actually what I've seen from artists that I've talked to, including the guys who are in that short little video clip I showed, they're enormously excited. They see this as an exciting new medium that they can work in and a new tool that gives them this sort of expressive power. Interestingly, in my experience, artists are much less frustrated than the technical people, including like the technical directors who work with the artists. The artists are the least frustrated by the sort of black box, unpredictable nature of the deep networks. They're kind of used to that. They're used to you throw paint to the canvas and see what happens. It's not that they don't want control, but they're much more able to kind of roll with the idea that this is not an entirely controllable process. They like that. They like the interactive exploration. So I don't think that we are ultimately replacing artists, or for that matter, actors, right? I think that it may be that acting becomes more important. In fact, that the actual performance part of acting is something that's much harder to replace than than what people look like, or how old they appear. I think you see that already. Yeah, I think that artists tend to be excited by these tools rather than offended by them. There's a related question. How could Nvidia make some of these tools more accessible to artists and help them realize that these tools can enhance their creativity? And so it's a little difficult because we don't make most of the tools that artists use, although we are increasingly starting to release some of these things in sort of toolkits. There's an Nvidia product, or I guess platform would be a better term, called NGX, which is a sort of a what's the word I'm looking for? Kind of a platform for us to release these sort of cool neural network inspired capabilities. But ultimately, I think it's to the tool makers, whether that's the artists or internal tools at film studios, or large companies like Adobe or Autodesk, to incorporate these concepts. And I think that's what's happening. Yeah, and certainly, most of this code, as I've said, most of what you see is released under a sort of non-commercial license, right? So anybody can download these things off of GitHub. We actually take some care to make them relatively easy to use, as easy as you can sort of make Python. And so the comment was made in the early development stage, and I think that's exactly what this is for, right? It's very easy for anybody to go and download some code or to experiment with Gauguin online, for example.
Okay, thank you very much, David.
Okay, what library do I suggest implementing AI-based rendering algorithms? Okay, so that's a good question. First of all, in deep learning, we're kind of agnostic as to deep learning frameworks. We've been asked to stop for questions. I'll get this idea. I'll get this last one out quickly. We're agnostic to frameworks. We use PyTorch, TensorFlow internally for the most part, one of those two. And there's a new thing called Kaolin, Kaolin, from Nvidia that you should search, which is a differentiable rendering package, which I think is a really interesting toolkit for people building new algorithms. So I see now that we should stop. So thank you, everybody.
Thank you, David, for a very nice
enjoy the rest of the conference.
I actually have one final question, if you can hear me. I was wondering, given all the very, remarkable results that we see from especially the deep learning type algorithms, are there any of the things that you have shown today that kind of surprised you when you, in terms of, the level of the results or the expressional power of the, models that you had trained?
Okay, sorry for the delay. There's a delay between when I can hear the question on YouTube and respond on Zoom. Absolutely, I'm shocked by how good StyleGAN is. I'm shocked by how well the neural light field worked, and I'm continuously surprised by how powerful these things are. It's almost every result I showed you I found surprising. This is completely against my intuition, and it's really causing me to rethink a lot of what I learned as a computer graphics person, like in my 30 years or whatever as a computer graphics person. So I really encourage everybody to dive headfirst into this new frontier. It's going to upend much of what we think we know about how to synthesize images.
And I think that we are all equally shocked about how good the results are. So I think this is a very good place to end this presentation. And once again, thank David Lübbecke for his presentation. Thank you.